Okay, so the cat is falling, it has no initial angular momentum. To turn its body, you need to have angular velocity, so you need to have some angular momentum. But angular momentum is conserved. How can you do that? You can do that by turning the tail in the opposite direction. So that the tail, let's say it is negative, will cancel the positive angular momentum of the cat's body, and then you can rotate by swinging its tail. Let's watch that in action.
For me, the perfect landing follows an excellent...
What is the point of playing this? This is from Nat Golf.
For me, the perfect landing follows an excellent in-flight movie, a delicious meal, and a light nap. But for cats, the perfect landing follows some mind-blowing mid-air acrobatics. They're famous for their ability to land on their feet, which is something we need to work on. Cats' legs extend under their bodies, acting as natural shock absorbers. Ours aren't as effective. But I think he knows that now. I bet that blew away the cobwebs. Is a falling cat's ability to always land on its feet myth, miracle, or a marvel of physics? Well, the law of conservation of angular momentum states that when a cat is falling, turning one part of its body means another part has to turn in the opposite direction. First, he orientates himself by turning his head, and then he arches his back. Next, he fully twists his front legs, whilst his rear turns in the opposite direction. To complete the turn, he twists his rear legs whilst his front turns in the opposite direction. Once again, he arches his back to reduce the force of impact. Mother Nature gave cats this innate ability to land gracefully to counteract a rather fundamental flaw. They're completely daft. You name it, they'll fall off. Muffin here has had the excellent idea of jumping on top of the door. Nowhere else to go now. What about the door frame? Great landing. In less than a second, Muffin turned his body, saving his neck and his dignity with a perfect four-footed landing. Tabitha has been trying to get the last crisp from the packet. This happened to me last night. Mind the edge! Oh, textbook tumble Tabitha. Even with a bag on her head, instinct kicked in and she managed to perform the perfect mid-air pirouette and land safely on her feet.
Alright, so that's how cats use angular momentum conservation to land on their feet. The last example for angular momentum conservation is called the Kepler's law. The Kepler's second law, to be precise. So you learn Kepler's first law is that the planet will orbit the sun in a orbit of ellipse. The shape of the orbit should be ellipse. I didn't go into that because that's too hard. So we did circular motion for the third law, which is t squared r cubed has to be a constant. The second law comes from angular momentum conservation. When the planet is on the orbit, gravity is attractive. So the lever arm and the force is making a 180-degree angle. When the lever arm and the force is making a 180-degree angle, how big is the torque?
0.
Good. So torque is 0, and L is conserved. Okay? Now, if you look at the speed of the planet when it is closer to the sun, and the speed of the planet when it's far away from the sun, you will see that the planet speed up as it gets closer with distance r1, and it goes slower when the distance becomes far. It is caused by angular momentum conservation. When it is closer, the moment of inertia is smaller, so angular velocity is bigger and it goes faster. When it is far, moment of inertia increases and the angular velocity decreases. So to convert angular velocity to the speed, we write down angular momentum. We write down the relation. Speed will be radius times angular velocity. So when you look at angular momentum conservation, it means that the moment of inertia at here equals at here times omega 1 equals the moment of inertia at here times omega 2. Okay. What is moment of inertia of this planet? Well, I equal. It's just a particle. So what's the moment of inertia for a particle?
R².
Good. So it will be the mass. The mass doesn't change, so it's r1 squared. Omega 1 equals m r2 squared omega 2. Mass doesn't matter. What you get is r1. r1 times omega 1 gives you the speed at this place. So you'll see that the speed and the distance to the sun is relative. If it is closer, the speed will be bigger because the product is a constant. Okay? So what Kepler's law is saying is somewhat different because he doesn't know it is angular momentum conservation. He stated as the area here and the area here will be the same if the time difference you're looking at is the same. So like the planet goes from here to here after some delta t, and the planet goes from here to here after some delta t. Now, the area is basically a triangle, and the length here will be the speed times delta t, and a smaller speed times delta t. How do you compute the area of triangle?
1/2 base times
1/2. So in this case, the base will be r2, the height will be v2 delta t, and for this triangle, you have 1/2 base becomes r1, the height becomes v1 delta t, and because r1 v1 equals r2 v2 due to angular momentum conservation, you get that the area is the same. That's Kepler's second law. It's just a consequence of angular momentum conservation. Okay? So again, I've just thrown this I omega formula to you. You have to memorize it. I'm not going to prove it because it's really hard and I don't want to torture you. The plan for our next lecture is to talk about North's theorem, which is the formal way of proving it. And we're not going to prove it because it's really hard. I'm just going to vaguely wave my hand to tell you how North's theorem show that angular momentum is conserved, energy is conserved, and momentum is conserved. And then we talk about some phenomena that Newton's law doesn't work. And that's it for the quarter, for the summer section. And if I have more time, I'll do some final review. So that's for next Tuesday. And the homework for this is due next Monday. The homework for Tuesday's lecture is due on Tuesday. It's short, there's no calculation involved. You just need to show up, and I will basically tell you the answer in the lecture because the question is like, how does North's theorem, why is North's theorem important? And tell me one phenomenon that cannot be explained by Newton's law. So you can just do your homework during the lecture, and before the lecture is over, you're done. Okay. And then you will have this Wednesday to prepare for the final, and final is on Thursday. Any question?
You said that there will be one midterm question on the final.
Yeah.
And then also like dimensional analysis question.
Yeah, that's problem 1 and problem 2
And then like 8 other questions.
from the final material.
Okay.
Any other question? Alright, if you have more or you want to play around with angular momentum, come here and try. Lecture is over.